Alright, so in this video we're going to talk about mechanisms. When we have a chemical reaction occurring and we're trying to get some information about its kinetics or how fast it's going to work, a mechanism is also something we're trying to obtain. From our kinetic information, we can make a mechanism, and a mechanism is a multi-step plan or pathway of how a reaction occurs. How do reactants turn into products? For a majority of reactions, this does not happen in one step. Like one giant collision of everything and boom, you have products. That normally doesn't happen. What happens is a series of collisions, a series of steps. And the steps have to go in a certain order and have sufficient energy at each step. So we're going to talk about how mechanisms are developed and how we can use them to find our kinetic information. Now when we look at a reaction mechanism, it is normally written as a series of steps. So we have step 1, step 2, step 3. So in this example, we have our balanced equation, 2a plus b goes to e plus f. We would only see A and B as reactants. E and F would be the products, and we wouldn't know anything about the kinetics or how it would make products E and F. But if we look at the mechanism, which is the 3 lines next to it, we see 3 steps. First, molecule A and molecule B collide to make C. Notice C wasn't in our balanced equation at all, so C is called an intermediate. It is a molecule that is created as a way to get to the next step. So we see in the very next step that C then collides with another molecule of A to produce D, which was also not in our equation. So D would be a second type of intermediate. And then in the third step, the D molecule is broken down into E and F. And this is where our product comes from. So it isn't until the third step that we even see our product from this mechanism. Now each of these steps in the mechanism is called an elementary step or an elementary reaction because it is the most basic reaction. We can't simplify it anymore. And you can have as many elementary steps or elementary reactions as are necessary for your mechanism. So you can have just 2 steps, you can have hundreds of steps. We're only going to look at fairly short mechanisms of 2 or 3 steps. But the idea behind it works out the same, regardless of how many steps you have. Having the steps help you understand how the reaction is progressing and where the kinetics come into play. So if we look at this example, in step 1 we have a molecule of NO2 and a second molecule of NO2 that have to collide to create an NO3 molecule and an NO molecule. Now this step is very, very slow based on what we can see in the laboratory. Step 2 takes that NO3, so in this case NO3 would be our intermediate, and it collides it with a molecule of CO to create NO2 and CO2. This step is very, very fast based on our kinetics. So when we add these 2 steps together, and we do this by adding everything on the left side together and then everything on the right side together and crossing out things that occur on both sides, we can see that the NO3 molecules would cross out, one of our NO2s on each side would cross out, to give us an overall balanced equation of NO2 plus CO produces NO plus CO2. So just looking at the balanced overall reaction, we would have no idea that this is a 2-step mechanism. But from the mechanism, we can get an idea about which step is very slow, which step is very fast, and what type of intermediates have to be made. When we look at each of these elementary steps, we also need to look at the kinetics of the individual steps. And we write these rate laws for each step just like we did the rate laws for the overall reactions. But because it's a mechanistic step that can't get any simpler, it's easier to write the rate laws. We don't have to rely on tables of data. Once we have the mechanism, which theoretically came from our data, we can then take that mechanistic step to write a rate law. So some vocabulary words. Molecularity tells us how many molecules have to collide in one step. So if a step only has one molecule that breaks down into products, this is called unimolecular. One molecule is necessary for this step. If, however, we have to have a collision between two molecules, this is called bimolecular. So the bi indicating two. So we need two molecules in that step. Now the two molecules can be the same type, both A, or they can be two different molecules, A and B. It's still called bimolecular for needing two molecules. Termolecular means we need three molecules to collide. So these can be three identical molecules, two identical and one different, or all three could be different types of molecules. We don't really see anything more than that. Having more than three molecules collide with sufficient energy and in the correct orientation really just doesn't happen. So we only have unimolecular and bimolecular a majority of the time. Termolecular comes up rarely. When we know whether we have unimolecular, bimolecular, or termolecular processes, we can then write the rate law. And the rate law is written as rate is equal to rate constant times the concentration of whatever molecule we have in the step. So if it's unimolecular, it's just the concentration of that molecule. If I have to have a collision between two molecules, then I have to multiply those two concentrations together. So this would be A squared if I'm having two molecules of A, or A times B if I have two different molecules. Termolecular, if I have all three are A molecules, it becomes A cubed. Or if I have two A's and a B, A squared times B. Or if all three are different, A times B times C. So in this case, the reaction orders are really just counting how many of the molecules you have in the reaction step, in the elementary step. So we don't have to calculate these. So let's look at an example. We have a 5-step mechanism for our overall reaction. For each step, we want to look at what the molecularity is and what the rate law would be. And then we want to get an overall balanced equation for what the reaction is. So let's look at the first step. 2NO produces N2O2. So I need two molecules of NO to collide in order to make a much more complex N2O2. So this would be A plus A, in this case NO plus NO, to make our product. So our rate law would indicate the bimolecular reaction as rate is equal to K times NO squared. Alright, second step, we have 2H2 producing 4 H's. Now if we look at what's actually happening here, I don't need two H2 molecules to collide to produce all 4 of these H's. One H2 molecule can produce H's. Alright, so the coefficients here can be simplified. Instead of 2 and 4, we can simplify this to 1 and 2. So I only need one H2 molecule to produce H's. So instead of this being bimolecular, because we have a 2 here, this is actually a unimolecular step, because I only need one molecule of H2, not two, to produce H's. Notice how that's different than step 1. In step 1, I needed both of these NOs to make N2O2. I can't make N2O2 with one NO molecule. I don't have enough. Alright, so in step 1, 2 molecules were necessary. In step 2, only one molecule is necessary. So step 2 is unimolecular. And this would be rate is equal to K times H2. Step 3, we're back to a bimolecular step because we have 2 different molecules that need to collide in order to produce N2O and HO. So this is bimolecular. Rate is equal to K times N2O2 times H. Fourth step, we have 2HO plus 2H gives us 2H2O. So you'll notice this is 4 molecules. And we said previously that term molecular was as big as it gets, so 3 molecules. So we know we don't have 4 molecules colliding. This one again is very much like step 2. I don't need 2 HOs and 2 H's to collide. I only need 1 HO and 1 H to collide to make a water molecule. So this is a case where my coefficients can be simplified. Instead of 2, 2, and 2, this would be 1, 1, and 1. So I would need 1 HO molecule and 1 H molecule. So step 4 is really bimolecular. My rate law would be rate is equal to K times HO times H. And then the last step we have bimolecular again, 2 different molecules, H and N2O, to produce our products. So rate is equal to K times H times N2O. So we know the molecularity of each step. We have bimolecular, unimolecular, bimolecular, 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 and we know the rate law for each step. So let's look at the overall equation then. We need to cross out things that are on the left and the right side. So we need to find our intermediates. So in step 1, we're creating N2O2, which is then used in step 3. So N2O2 can be canceled out as an intermediate. We're also producing H's in step 2, and we have 4 H's, and notice all 4 of those get used up. So in step 3 we use up 1, in step 4 we have 2, in step 5 we use 1 again. So all 4 of the H's cross out, so that would be another intermediate. N2O is produced in step 3, and then used up in step 5. So that's an intermediate. And HO produced in step 3 is used up in step 4. Notice we are also producing it in step 5, but both of these HOs get used up, so they cancel out. So what did we make that we didn't cancel out? So we have 2 water molecules that we cannot cross out because we don't have any water on this side. And in the last step we produced N2, which also cannot be canceled out. So 2H2O and N2 are our products. If we look on the left side, what are we using that is not an intermediate? So we know that N2O2 is an intermediate, HO is an intermediate, the H's are intermediates, and N2O were. The only things on this left side that are not canceled out are the NO and the H2, and these are our reactants. So our overall chemical equation is 2NO plus 2H2 produces 2H2O plus N2. So why is it important to have each step and to look at the kinetics of each step? What is that telling us? Well, if we look at a multi-step process, Knowing the kinetics of each step actually tells us the governing principle behind the entire reaction. The slowest step of a mechanism represents the speed of the entire reaction. We can't go faster than our slowest step. So in the picture we have an example of toll plazas. As cars approach each plaza, they have to slow down. So in the first picture, they're slowed down at Plaza A, and then once they get through Plaza A, they're flying through Plaza B. So really, the slowdown at Plaza A determines the speed of your trip. Or you could be slowed down at B, so getting through A doesn't slow you down at all, but then you have to slow down for B. So the rate of your car moving through the plaza, moving through the toll region, is based on moving through Plaza B in this second picture. So if we think of the same thing with chemical reactions, is our reaction slowing down at step 1? Is that the slow step, taking the most time? Or is it flying through step 1 and step 2 is really slow? Alright, so looking at the kinetics of each step can tell us about which step is the slowest. The slowest step is called the rate determining step. It dictates the rate of the entire reaction. And this is important because the rate law of that slow step is the rate law for the entire overall equation. Alright, so let's look at the first step being the slow step. So in our earlier example, NO2 plus CO produces NO plus CO2. We have a two-step mechanism. So previously we looked at NO3 being our intermediate, gets used up in step 2 to produce our products. And we were given the information about which step was fast or slow. In this case, we have the slow step written as step 1. So if step 1 really is our slow step, then the rate information comes from step 1. And we would say that rate is equal to K times NO2 squared. CO being only in step 2 is therefore not part of the reaction rate because it's not part of the slow step. It's not part of the rate determining step. So where our NO2 is second order, our CO would be 0 order. Its concentration doesn't affect rate because it's not in the slow step. Right, so when we're creating our reaction mechanisms to tell us our kinetic information, we need to remember there's 3 different requirements for a mechanism to be successful. The first is that all of your elementary steps have to add up to the overall reaction. You can have as many steps as you want, but you have to make sure they all add up to the same exact balanced chemical equation. Number 2, all of your steps should be either unimolecular or bimolecular. Very rarely can you have a termolecular molecularity, and nothing greater than termolecular is allowed. So when you break down your reaction, you have to make sure that all of your steps are either 1 molecule breaking down or 2 molecules colliding, and at the very worst, 3 molecules colliding. And then the third rule for our mechanisms is that the rate law of the slow step has to equal the rate law for the overall reaction. So when we get our kinetic information and we find out which step is the slow step, that has to make sense for our mechanism and for what we see from our overall reaction.